Hello guys, today we are going to talk about how do we determine the convergence. So in our previous topic, in our previous lecture, we talked about the convergence and divergence, but today we'll be talking about how we can just determine this convergence. So we're going to start with some examples over here. And our first example is we have a series that is 1 by 1 square plus 1 by 2 square plus 1 by 3 square, right? Up to so on, right? What do we do? We have this table against those values, right? We have the values of n, and then we have this values of particular series, right? We can clearly see when we start from 5 and we end over 5,000, right? Our values are continuously increasing and approaching to a particular value, right? Which means that this particular value is being convergent. The series is being convergent, right, with the help of these values. All right, we have another example over here, and we can see in this example it is 1 by under root 1 plus 1 by under root 2 plus 1 by under root 3 and up to so on, right? All right, so again we have examples over here in the form of table, right? We have these values. So our value is starting from 5. Our value of n is starting from 5 and goes to 5,000, right? Opposite to that, against these values, we can see there are particular values of the series, but these values are not helping at all to provide some sort of convergence, right? So we cannot see that there is a convergence on a particular point. So this is actually you can see we have this particular series over here. The A series is 1 by 1 cube plus 1 by 2 cube plus 1 by 3 cube up to so on. It means that this is convergent series because it's a P series with the value of P is equal to 3, and that is actually greater than 1, right? Okay, on the other hand, we have this B series, and in our B series the values of our series are 1 plus 1 by under root 3 under root 2 cube root 1 plus 1 by cube root 2 1 plus 1 by cube root 3 1 plus 1 by cube root 4 and up to so on. It means that this particular series is divergent because the values of P are 1 by 3, right, which is already less than 1, so it means it's divergent. Okay, now the comparison test. This kind of test is actually significantly used to determine whether or not series converges or diverges, right? So to use convergence test, first we have to realize that our original series should be called an, right, or a sub n. So this series has to be called a sub n, and with the help of this series we will be finding our b sub n, right? And after that we'll be able to find any sort of comparison between these two series, and then we'll say that whether this is convergent or not, or divergent. So in comparison test, the idea is to compare a given series with a series that is known to be convergent or divergent, right? So it's same like a sub n and b sub n things. We have to have this a sub n, and later we'll be able to find b sub n with the help of our a sub n. So over here we have this a sub n, what that is 1 by 2 and 2 raised to power n plus 1, which is less than 1 by 2n, right? It shows that our given series has smaller terms than those of the geometric series, and therefore all the partial sums and all smaller than the sum of geometric series. All right, so let me tell you one thing clearly, that our b sub n is often a geometric series or p series, right? So here in this case we have this b sub n is actually geometric series, right? We can see over here, and it says if this is geometric series and its sum would be also greater than the sum of this series, which is a sub n, right? And these would be less than, both a sub n and b sub n would be less than 1, so we have this particular series convergent in this particular case. Okay, now the following test applies only to series whose terms are positive. All right, now what do we do in our comparison test? Suppose that we have our a sub sigma a sub n and b sub n are a series with the positive terms. It means that both of the series must be greater than 0, right? They should not be less than 0, understand? If sigma b sub n is a convergent and a sub n is less than or equal to b sub n for all n, then a sub n is also convergent. So it means that our b sub n will determine whether the a sub n is convergent or not. And for this particular thing, we have to have our a sub n less than or equal to b sub n, right? And our b sub n will be determining that our a sub n is divergent, right? Because if our b sub n is divergent, our a sub n would be definitely divergent, and we will have this particular condition that our a sub n would be greater than or equal to b sub n. So clearly in the first part says that if we have a series whose terms are smaller than those of a non-convergent series, right? We have our series which is a sub n and its terms are smaller than those of non-convergent series, that is our b sub n, then our series is convergent, right? So the second part says if we start with a series whose terms are larger than those of the non-divergent series, then it is true divergent, right? Okay, in using the comparison test, we must of course have some known series, that is sigma b sub n, for the purpose of comparison. Definitely we have to have b sub n, otherwise we will not be able to compare, right? So it would be in two forms, I told you before, p series or geometric series. So for p series, it would be it will be convergent, or it will converge if the value of p is greater than 1, right? And it will diverge if the value of p is less than or equal to 1. Whereas if we have the geometric series, if our b sub n is in geometric form, we have to know the convergence would be when we will have our r less than 1, and divergence would be when we will have our r greater than or equal to 1, understand? So we have an example over here, and it says determine whether the series this converges or diverges. So you have to find actually what happens to this particular series. So please give it a try and then we see. Okay guys, so we have this particular series over here where our sigma 5 by 2n square plus 4n plus 3, and our n is equal to 1 over here, and it goes towards the infinity, right? Okay, so for large n, the dominant term of the denominator is 2n square. Okay, now let me tell you how do we actually determine our b sub n, right? So what do we do? In order to form our b sub n, we will take the terms from the numerator and denominator that have the greatest effect on the magnitude. So here in this particular example, we have 5 in our numerator, that is the only value, right? So we will take this 5 as a numerator for our b sub n. And here in the denominator of a sub n, we have 2n square, which is with highest magnitude, right? So we will take this 2n square as a denominator of our b sub n value, right? So you can see over here, it's clearly 5 by 2n square, right? And why this is greater than our a sub n, right? Since you can see the denominator of our left hand side is bigger, so whenever we have this denominator bigger, our value would be smaller, right? So it clearly means that our a sub n is smaller than b sub n, right? And in notation of the comparison test is a sub n is the left side and b sub n is the right side. So we have to keep this thing in mind whenever we are going to write our notation. Our a sub n would be on the left side and b sub n would be on the right side of our equation. So we know that You can see over here, now we have this sigma 5 by 2 n square where n is equal to 1 and goes towards infinity, right? Now we're gonna take this constant out here, 5 by 2, right? Sigma n is equal to 1 and goes to infinity, 1 by n square. Now it is convergent. Why is it convergent? Because the value of p is actually 2, right? And what did we study in our beginning of the p series? That was, it will be convergent when we will be having the p value greater than 1, right? And it will be divergent when we will have our p value less than or equal to 1. Understand? So it's clearly convergent over here, right? So therefore this is convergent by part 1 of the comparison test. All right, we have a note 1 over here, which is although the condition a sub n is less than or equal to b sub n, or a sub n is greater than or equal to b sub n in the comparison test is given for all n, we need to verify only that it holds for n is greater than or equal to capital N, where capital N is some fixed integer, because convergence of a series is not affected by a finite number of terms. So the convergence of series is actually not affected by the finite number of terms. Okay, here is a note 2 that says terms of the series being tested must be smaller those of the convergent series or larger those of the divergent series. Okay, so I mentioned earlier our b sub n would be greater than our a sub n, right? And if the terms are larger than the terms of convergent series are smaller than those of the divergent series, then the comparison test does not apply. Yeah, so if it's inverse of this situation, then we will not be able to apply our comparison test over here, right? Okay, consider for instance the series is something like this. All right, it means that our sigma 1 by 2n minus 1 n is equal to 1 goes to infinity. The inequality is 1 by 2 power n minus 1 is greater than 1 by 2n 2 power n, right? So it's going to be useless to apply this test, because as we know that if our a sub n is greater than our b sub n, right, this test would not be applicable. So in that case, what do? We will have our limit comparison test. So what does it says? The limit comparison test says, suppose that we have sigma an, right, and sigma bn. These are the series of positive terms. These are the series with positive terms, right? Okay, so here is the deal. Our limit a sub n divided by b sub n is equal to c. C is a constant over here, and then our n approaches towards infinity, right? Now remember, if our c is greater than 0, the either both series converges or both diverge, right? Okay, let's see in this example number 3. It says test the series that is sigma 1 by 2 power n minus 1 and n is equal to 0 and goes towards infinity, and you have to see whether there's convergence or divergence in the series. Okay, so now, okay, first of all, please try to do it yourself, then let's see what's the answer, or what's the answer be like. Okay guys, so coming up with solution. My bad, I'm sorry. Here we use limit comparison test, and in limit comparison test we know that we have to use a sub n and b sub n. Or a sub n would be 1 by 2n minus 1, and when we form our b sub n, that would be, we will taking the highest terms from the numerator and denominator. So you can see the highest terms in the numerator is 1, and the highest term in denominator is 2n, 2 power n, right? So we just formed our b sub n, and we have the value of b sub n over here. I'm sorry guys, this is actually this was the part of an image. I think it's disturbed, but I'll send you the PPT and you can see it clearly, but I am gonna explain it to you because I can see it on my laptop as well. So what do we do over here? You'll be able to see that we'll have limit a sub n by b sub n, and where n is approaching to infinity, right? So we will just put the values over there, right? We'll plug in the values of a sub n and b sub n, and we'll be able to know that it's equal to 2 power n by 2 power n minus 1, because these values will be actually inversed. These are being divided. You can see 1 by 2n, 2 power n minus 1, and 1 by 2n. These would be inversed when we will divide both of them, right? So we will have a value 2n by 2n minus 1. So when we will be just, we will because you are not able to see the picture over here, right? When we will solve this for the limit, we will be able to see that it's equal to 1, right? And if it is equal to 1, it is definitely large and greater than 0, right? Since this limit, all right, yeah, so this limit exists actually, right? And sigma 1 by 2n is a convergent geometric series that the given series converges by the limit comparison test. So the things varies. So when we have this kind of situation, we're going to use our limit comparison test, right? Because we will not be able to solve it with our normal comparison test. Okay guys, after that, now we are able to see that the another form of our comparison test, that is ratio and the root tests. Okay, so what is ratio test actually? We're gonna replace in this particular test, I'm gonna just give a little summary of this test, and then we will be able to find what do we do with that. So in this particular ratio test, we're gonna replace the variable k with our k plus 1. We have a variable, right, in our example, and we will be able to replace that with suppose we have a k variable, and we'll be able to replace that with k plus 1 everywhere we see k, right? Then we will simplify and solve for the numbers, and the number is gonna be equal to what we call L. Okay, and whatever value we get for L, that determines whether the series converges or diverges. All right, so I mentioned we will have the value L over, so you can see over here, if our L is less than 1, right, the series is absolutely convergent. Okay, and if our value of L would be greater than 1, it means that series is divergent, understand? And if the ratio test is if the value of L is equal to 1, it means that the ratio test is inconclusive. That means we will not be able to conclude this particular test, and we cannot just draw whether the result is about convergence or divergence of this particular series, right? So these are the three conditions we have in our ratio test. What do? We have to find actually the value of L, and if our L is greater than 1, it means it is divergent. If our L is less than 1, it means it's convergent, and if it is equal to 1, it means that it's inconclusive. We cannot find any kind of conclusion for this series. All right, so since we talked about this inconclusive thing, first of all, we're going to address our part number 3, that is in the ratio test, if the limit where n is approaching to infinity, an plus 1, a sub n plus 1 is divided by a sub n is equal to 0, right? That gives no information. It means that we don't have any kind of result. So for instance, for the convergent series sigma 1 by n square, we have, okay, now what do we do over here? We just gonna simplify this, and we see whether it is right or wrong. So what do? We will just add our we will add 1 to our I'd say I mentioned we will add 1 to our variables, right? So you can see a sub n over here, and we will be adding a sub n plus 1 over here, and we will divide a sub n plus 1 by a sub n, which is the actual value over here, right? Now this is our a sub n actually. All right, so when we are going to add these values over here, you can see this is absolutely 1 divided by n square and n plus 1 whole square, right? This whole will be divided by 1 by n square. Okay, now the easiest thing, whenever we have this kind of situation, that means if we reverse it, we will be able to multiply it, right? So this thing will be, this thing n square will be coming up over here, and this 1 will be down. It will become a denominator, right? Okay, so it would be equal to n square by n plus 1 whole square, right? And then it will be equal to 1, understand? Right, now you can see over here, and then we will have this value over here. In the denominator, we will have 1 plus 1 by n whole square, and this will actually equal to 1, because if we just simplify it, we'll plug in the values. It means that 1 by infinity, right? Because n is approaching to infinity, and it will become 0 over here. So 1 plus 0 is equal to 1, right? And 1 by 1 is equal to 1. So it means that our answer is L is equal to 1 over here, which means it is inconclusive, right? Whereas the divergent series, okay, now this thing was actually for convergent series, right? Now we're talking about divergent series, where we have our sigma 1 by n. Sorry guys, my bad. Okay, so you can clearly see over here, what do we do with the original series? We just added plus 1 with the variable over here, right? Again, we made the same thing. And now this time we have 1 by n, right? Okay, by simplifying that, we will find n by n plus 1 over here. So what do? We just simplify it further, right? We have 1 by now. If you are curious about how we're just getting these values, so let me tell you, we will just divide this with the highest value, with the highest I'd say term. We have this highest term over here, so we're gonna divide the whole particular series, right? And then we will be able to find this value over here, right? So if you are confused how did we get this one, we are actually going to divide this. Suppose we have this n is the highest or biggest term over here. We're gonna divide whole of this series, right, with n. So if we divide n by n, we will get 1. If we divide n by n, we will get 1. If we divide 1 by n, we will be getting 1 by n, right? So that's how we get this value. So do not be confused about this thing. Okay, now here, this is actually going to be equal to 1, because 1 by 1 plus 1 by n, right? 1 by n is actually our infinity, because it's 1 by 0, and whenever we have the 0 as denominator, that would be equal to infinity, right? So if we add 1 to our infinity, that would be again infinity, right? So what do? We just get 1 over here, right? So therefore, if this limit is equal to 1, the series might converge or it might diverge. In this case, the ratio test fails. We must use some other test, right? So ratio test will not be applicable in this particular I'd say case, right? Okay, we have two examples over here and we'll be going through one by one. I just encourage you people to try it on your own, and if you're not able to do it, then we will be trying to solve it, right? Okay, please do it. Okay guys, now we just attempt it together. Now we have this series number one over here, equation number one, and we will be trying to solve it down. Okay, coming up with solutions. As I told you, you have to just add one to your variables. Wherever you see your variable in the particular term, you will just add one, right? And then we will divide that with our original value. Okay, so this happens over here. We have the original value is 2k by k factorial, right? 2k by k factorial. So what do? We just add 2k plus 1, right? I told you you have to replace your variable with that variable plus 1. So we have this 2k and k is a variable. We will replace this variable k with the k plus 1. Okay, now as a denominator we will get k plus 1 factorial, right? We had k factorial, so we'll do it k plus 1 factorial, and we'll divide this by 2k by k factorial. That is our original value. Okay, now in the next step we will be able to multiply these two values, right? We can multiply these two values as well. So when we multiply them, it would be something like that, right? 2k plus 1 by k plus 1 factorial, understand? And then we'll multiply it by k factorial by 2k. Okay, now what do? We will just attempt to have our exponents. We will solve our exponents with the same basis, right? And if we attempt to solve them, we'll be able to do something like that. Okay, we will move our 2k down there as a denominator and 2k plus 1 over there. So if we will try to attempt this one, we will just cancel our k with k, and our power would be just 1 on the 2. So it will be only 2 over here. You can see, right? Only 2 over here. Okay, now how about the factorials? About the factorials, let me give you an example. Suppose we have 5 factorial. Instead of this k factorial, we have the 5 factorial. Okay, so what do? We actually solve it by 5 into 4 into 3 into 2 into 1. That means that we'll be multiplying that with the lowest values of that, but lowest value than that particular value, right? So if we have 5, the lowest values are 4, 3, 2, 1, right? Until 1, these are the lowest values for the non-zero lowest values. So we have to solve that factorial in this way. Okay, over here it's a bit different, right? Another way of solving this factorial would be k. Suppose that is 5 factorial. So what do? We will just write down 5 into 5 minus 4. I'm sorry, 5 minus 1, right? Into 5 minus 2 into 5 minus 3 into 5 minus 4, right? So it means that it is the same thing, 1 2 3 4 4. So that's the same thing. So we're gonna apply that particular method over here. For the factorial, we will just write down k over here, and then k minus 1, k minus 2, k minus 3 up to infinity, right? Then we have this k plus 1 over here. So we will write down k plus 1, and then again factorial k and k minus 1, k minus 2, k minus 3 up to so on, right? So simply we just gonna cancel this one with the numerator, right? And the remaining would be k by k plus, and the remaining would be k plus 1. So it would be equal to 2 by k plus 1, which is when we see that k is approaching to infinity, right? It means infinity plus 1, 2 by infinity plus 1, right? which is 2 by infinity. And whenever we have infinity as denominator, that means is equal to 0. So what happens over here, my dear fellows, it's less than 1 and it's convergent, right? Okay, we have another example over here, that is example number 2. And in this particular example, we have this limit, right? We again gonna get this get it upside down, right? We will just add it, then we're gonna multiply it over here, and after multiplication we will just find it that n plus 1 by 10, right? And then we will have our n that is going to infinity. Infinity by 10 would be also infinity, right? So because when we have the numerator as infinity, that would be going, and whatever the value is down there, the answer would be equal to infinity. That means if it is going to infinity, that is clearly greater than 1 and it is divergent in that case. Okay, something is bad over here, and I don't know what happened over here, but still we have this test of convergence. We have to see whether the series is convergent or not, right? So let's see, this is the solution of that particular series, right? Since the terms a sub n is equal to n power n by n factorial, right? These are the positive, we don't need to absolute value signs. Yeah, so if we have some negative values, we have to absolute those particular values in order to bring them in positive values, right? So what do? We just straight away following that procedure, we will write plus 1 with our particular variable over here, right? And then we're gonna multiply, since we will divide it, and in the reverse we will multiply these particular values over here, a sub n and b sub n, right? And after solving them, we'll be able to find that we are approaching to this e, because our n is approaching to infinity, right? Since our e is greater than 1, the given series is divergent by the ratio test again. All right, okay, so although the ratio test works in example 5, an easier method is to use a test for divergence, since we have this particular thing, and then we will just, we just gonna follow it. If it does not approaches 0 as an infinity goes and goes towards infinity, sorry guys, my bad, I'm fasting today as well. So therefore the given series is divergent by the test for divergence, right? Okay, then we have this root test again. Okay, in the root test, there's, if our value is equal to L, okay, and L is greater than 1, less than 1, it would be convergent. If L is greater than 1, it would be divergent. And if L is equal to 1, the root test is inconclusive, right? It is similar to that thing. So if our limit with n approaches to infinity, and the root n, a sub n is equal to 1, right? The part 3 of the root test says the test gives no information. If it is equal to 0, it will not give any kind of information, right? A series sigma a sub n could converge or diverge. So if L is equal to 0, L is equal to 1 in the ratio test, do not try the root, because this test will not be helping you at all. Understand? If L is equal to 1 in the root test, do not try the ratio test, because it will fail too. Okay, so we have this root test example over here. Please try to attempt on your own, and then let's see what's that particular solution. Okay guys, so here we go with the solution and attempt it together. All right, so we have this a sub n that is equal to 2n plus 3, and 3n plus 2 whole n whole power n. Okay, so what do? We will just simplify it down over here in this form, right? And write it down, or under root n a n is equal to 2n plus 3, 3n plus 2, right? And when we simplify it down, we will have some sort of simplifications over here. 2 plus 3 by n, 3 plus 2 by n, and that goes to 2 by 3, and 2 by 3 is actually less than 1, which means that our value, our series is convergent over here. So the given series converges by the root test. So it's proved that this series is convergent and it will be converging with the help of this root test. So that's all from today, guys. And if you have any kind of problem and question, please just ask me anytime. All right, though we will not be able to attempt this question and answer session today, but still you can ask me any question anytime, and I hope this is pretty much clear to you people. This is not a big deal. I mean, this was an easy topic, right? And sorry for the delay of this topic, but still come up with the questions if you have. Thank you so much, and bye till